Okay, so welcome back, and now we're going to talk about one-sided limits again. But this time we're going to be more precise. So we're going to introduce the epsilon delta definition for dealing with limits from the left and limits from the right. So let's read. It says limits from the right, okay? It says let f of x be defined over an open interval of the form a comma b, where a is less than b. Then, the limit as x approaches a from the right of f of x equals L if, for every epsilon greater than 0, there exists delta greater than 0, such that if this is true, if x minus a is greater than 0 and less than delta, then the distance, the absolute distance, right, the distance from the function and L will be less than epsilon. Okay, very similar to the definitions that we talked about before, except notice that we don't need the absolute value sign here because we're talking about one-sided limits. Okay, and since we're approaching from the right, this is all we need. Okay. Also notice that here we're only interested in approaching A because A is less than B, so we're approaching from the right. Okay. Now the limit from the left is defined very similarly. Let f of x be defined over an interval, or an open interval of the form b comma a, where b is less than a. Then the limit as x approaches a from the left, so now we're going that way, of f of x equals L if for all or every epsilon greater than 0 there exists a delta that's greater than 0, such that if x minus a is greater than negative delta and less than 0, so now again we're on the other side, then the absolute value of the function minus L is less than epsilon. Okay? And so now what we're going to do is we're going to apply this definition to an example. And again, this is just another example of being more rigorous when we do our definitions. Okay? And this is what calculus is all about. As you get in the higher level math classes, we become more rigorous in our definitions and our theorems. And our proofs, okay? Because it's important to be exact in our language and more rigorous in our proofs because, again, mathematics is the foundation of, well, in my opinion, the foundation of all the hard sciences, okay? Talk about physics, chemistry, engineering, you know, mathematics is the foundation where those applications come from. A lot of the stuff that we develop in math, in calculus and beyond, a lot of these things, these theories that these famous mathematicians came up with, found applications later on in the hard sciences like physics. So it's important to be exact because, again, we want to be precise in our language so that there's no confusion. And so that's why we do this in mathematics, is so that it's very easy to understand and follow logically. Okay, not the only reason, but a big reason. Okay, so that's it. So we'll do an example and see how this works.